So we've been talking about operators, linear operators on vector spaces, and we said the first thing you wanted to learn about an operator were its rough features, like what is its null space and what is its range. And we've studied those subspaces because both the null space of an operator and the range of an operator are subspaces of the vector space in which this operator acts. Now we want to proceed and ask more questions about this operator. So you're given a linear operator T that acts on the vector space, and you want to know more about it. So the thing we're going to study is that there's a question you can ask about these operators that leads to a very famous concept, the concept of an eigenvalue and associated eigenvectors. So that's the subject that we're going to discuss now, eigenvalues and eigenvectors. And this refers to some linear operator on some vector space. And we can ask, why do we care about these things? Well, we're trying to learn more about an operator. And in fact, since we've mentioned that in quantum mechanics, those operators play the role of observables, whenever you have an eigenvalue, it will tell you something about the observable. In fact, an eigenvalue will be a possible value of a measurement of that observable. Similarly, an eigenvector of the operator will correspond to the physical quantum state associated with measuring a particular eigenvalue. So these are crucial properties in quantum mechanics, and therefore we are taking our time to understand them mathematically. So what we're trying to understand is still how an operator T, that means that belongs to the linear space of V, how this operator acts on the vector space. So we mentioned there's a null space, there's a range, and in particular, we can now discuss another kind of spaces associated to this operator. And this will be called invariant subspaces. So what is the invariant subspace of an operator? Well, if you have that the operator acts on a vector space, you can ask, is there some smaller subspace of the vector space in which when the operator acts, you're not moved out of that subspace? So that's an interesting question because, for example, there will be interesting spaces like that, invariant subspaces. There are invariant subspaces that are a little trivial in that they kind of represent this idea but in a degenerate way, and some subspaces that are really quite interesting. So let me first state clearly what is an invariant subspace. So we'll call U an invariant subspace of V if, I will write it as T of U, so what is T of U? Is the set of all vectors T acting on U. If T of U is the set of all vectors T of U, where U, little u, belongs to the vector space U. So this T of U is what you get when you let the operator T act on any vector in U. So U is a subspace, and it is called an invariant subspace if this is a subspace of U. So it's contained within U. It doesn't take you out of U. So you act with the operator T on these vectors in the subspace U, and then you remain within U. So here we go. So the notion of an invariant subspace is always associated to some operator. Like, if I don't give you an operator, it's not invariant under what? So you should say what is invariant under. So there are two trivial examples of invariant subspaces. The zero vector, okay, is just one vector, and it's a subspace. You add 0 to 0, you're still 0. You multiply by a number, it's still 0. And any linear operator acting on the zero vector gives you the zero vector. So it is left invariant. You don't go out of the subspace. If you start with the vector 0, you cannot act with a linear operator and create a vector. So 0 is an invariant subspace. The full vector space is also an invariant subspace, because if you act with the operator on the full vector space, you still remain within the vector space to begin with. So those are kind of simple invariant subspaces, and they're not that interesting. So what could be an interesting invariant subspace? Well, let's think of the dimensionality. The zero vector was of dimension 0. It doesn't generate a subspace. The full vector space is a full dimension. So it may be more interesting if we get invariant subspaces of dimensions that are neither 0 nor the full dimension of the vector space. So let's consider one-dimensional invariant subspaces. So one-dimensional subspaces. Of V. So for these one-dimensional subspaces, let us take a single vector. Choose one vector, U, belonging to V, and then consider a space generated by this vector. So how is that possible? Well, if you have a vector that points in one direction, you can multiply it by a number, and you can make it bigger and bigger, or negative number, and you can make it in the opposite direction. You have a whole collection of vectors that form a subspace. If you add one here to another one, you get one still in the same direction, and you include the vector 0. So the set of vectors, and we will write it as capital U equal CU, the set of vectors CU, where C belongs to the field, real number of complex numbers, is a one-dimensional subspace. Subspace space of V. One dimension because it says one basis vector, and the span of that basis vector is the space. You multiply by a number, and that's the span. Now, it's important to emphasize here that we should choose U different from 0. A vector, this is a 0 vector, is just a little too trivial, and it will not generate a one-dimensional subspace because the 0 vector, however much you multiply it, never grows. So the 0 vector is no good. And here you've got now a one-dimensional subspace of V. Now, what is the condition that this subspace be invariant? When is it invariant under T? Well, it's invariant under T if T acting on this vector U is still in the subspace. So it's a number times the vector U. So it's invariant. When is it invariant? It is if T acting on U is equal to some number lambda times U, where lambda belongs to the field again. So this equation is so important that two names appear from this equation, eigenvalues and eigenvectors. Let's think of them, these two things, slowly. Take our time. So this is an interesting equation, and now we try to state clearly what these objects U and lambda mean or are. This is a reasonable equation. You're searching for vectors that are invariant up to a scale under the action of T. Therefore, the span of these vectors is a subspace that is left invariant by the operator. So what is lambda? We say that lambda is an eigenvalue. Lambda is an eigenvalue of T if the above has a solution with some U different from 0. So this equation, you see, if U is 0, this equation is trivially satisfied. T on 0 is a 0 vector. Lambda on the 0 vector is 0. So it's satisfied, and it's satisfied for any lambda. So U equals 0 is satisfied for any lambda. It's not an interesting equation. So we say that lambda is an eigenvalue only if there is some non-zero vector that does that. And in fact, this goes back to our intuition. Only if you have a non-zero vector associated to this vector, there will be an invariant subspace. So we need that there is some U different from 0. On the other hand, once you have this, well, let me say one more thing. If U is different from 0, it's necessary for lambda to be an eigenvalue. But lambda could be 0. There's nothing wrong with a lambda that is 0. In fact, in many cases, lambda equals 0 is a very interesting eigenvalue. And it's not a trivial equation, because if lambda equals 0 is an eigenvalue, you still have to find some non-zero U that is killed by T, because T on U should be 0 if lambda is 0. So you must find some vector that acted by T gives you 0. So lambda equals 0 is possible. So lambda equals 0 is allowed. Now, suppose you found an eigenvalue, then you have a non-zero U that solves this equation. Then take that non-zero U and then form its span. So the span U, the set of all vectors CU with C in the field. And every vector here is called an eigenvector. It's a little abuse of language, but anything, any vector in the span of U is called an eigenvector. That seems reasonable. If you have an eigenvector twice, that vector is the eigenvector 3 times minus the vector is an eigenvector. If you have a u that is non-zero here, you multiply it by any number, and it's still a solution of this equation. The thing is, of course, that the span of u includes the zero vector. So in that sense, we even may say that the zero vector is part of this eigenvector. Any representative here is an eigenvector. So this allows us to say things like the eigenvectors are the vectors in the span of u. And we even, in order not to say except for the zero vector, well, if it's in the span of u, including the zero vector will not harm you. But the interesting eigenvectors are the non-zero ones. But in terminology, all of this is called an eigenvector. Now, it may happen, a funny thing may happen, that for some particular values of lambda, you're trying to solve this equation, you may find that there's more than one vector, more than one linearly independent vector that solves this equation. You see, if u solves it, 2 times u solves it, but that's trivial. But it may be that there's a u that has this value of lambda and a different vector u that has that same value of lambda. So in that case, you have what is called the degeneracy. For a given eigenvalue, there's more than one eigenvector. In that case, the invariant subspace is bigger because the span of whatever vectors have the same eigenvalues is the full invariant subspace. If you have 2 vectors, for example, u1 and u2, that have the same eigenvalue, the span of u1 and u2, any linear combination of them, will have the same eigenvalue by linearity of this equation. So you'll get a larger invariant subspace. So when you have a degenerate eigenvalue, something that you have more than one eigenvector for a given lambda, the invariant subspaces get bigger and bigger. That brings in interesting complications, but there's lots of interesting physics associated to it. So we can summarize it by saying several linearly independent if there are several linearly independent eigenvectors for a given lambda, for a fixed lambda, we have a degeneracy. And a larger invariant subspace. So the subspace gets bigger. More terminology, the set of eigenvalues of the operator is called the spectrum of the operator. So if you have an operator T, its spectrum is the set of eigenvalues, the set of all solutions of this equation, all the lambdas that solve this equation for some non-trivial use. So the spectrum is the set of eigenvalues. So this equation can be written in a slightly different way. The equation can be written as T minus lambda times the identity operator acting on u is equal to 0. So that's the same equation. So we learn from this is that what is the condition that there's an eigenvalue is that there's a non-trivial solution of this equation, that there's a non-trivial vector, non-zero vector, that is killed by this operator. Then you have an eigenvalue. And therefore, the condition that you have an eigenvalue is that this operator is not injective. Lambda is an eigenvalue, means that t minus lambda I is not injective. And an operator is not injective if it has a null space. If it has non-trivial vectors that are being killed by it. So lambda is an eigenvalue if t minus lambda I is not injective, and in the case of finite dimensional vector spaces, finite dimensional, it means not that this thing is not injective, implies that it's not surjective, and it also implies it's not invertible. T minus lambda I not surjective, and it's not invertible. So those are the properties that must be satisfied by the nulls, by this operator t minus lambda I. So what are the eigenvectors of the operator? Well, the eigenvectors are those things that are killed by the operator. So the eigenvectors of t is equal to the null space of t minus lambda I. Vectors of t with eigen, let me make it more precise, with eigenvalue, value lambda. So if you have eigenvectors with eigenvalue lambda, are those vectors killed by this? So it's the null space of t minus lambda I. And that way, you see why we want to include the zero eigenvector, because the null space of any operator includes the zero vector. So it would be a headache to be having trouble with the zero vector all the time. So we include it as one more possible eigenvector. So let's conclude this first view of eigenvectors and eigenvalues with some remarks, some simple remarks about this. What is remarks? Let's connect to the idea that lambda equals 0 is allowed. So since lambda equals 0 is allowed, what are those things? Those are the vectors killed by u, by t, when lambda is equal to 0. So the eigenvectors for lambda is equal to 0 is the null space of just t, a very simple thing. So this null space of the operator actually is nothing else than the eigenvectors that have eigenvalue 0. So null of t is equal to the eigenvectors with lambda equals 0. Finally, one more comment. We've been talking about matrix representations of operators and how we can visualize operators concretely. But matrix representations, as we saw, depend on the basis that you choose to represent the operator. So they're basis dependent. They're not something that, well, some properties of the matrix representation may be basis independent, as we saw the trace is, the determinant of an operator is as well. But some things just depend on the basis you choose. And therefore, you could ask here, is this whole discussion basis dependent? And I think it should be clear that it's not, that the eigenvalues and the eigenvectors don't depend on the basis you choose to represent the operator. They're properties of the operator. Nowhere here we had to choose a basis. The concepts were all perfectly defined without using a basis. So the eigenvalues and eigenvectors of an operator are basis-independent quantities. Lambdas and eigenvectors are basis-independent quantities. So are the concept of invariant subspaces. This invariant subspace doesn't depend at all on a basis. You're just searching for what are the collection of subspaces of the vector space that when the operator acts on them, you don't get out of those subspaces. And that's a perfectly well-defined notion. So at the end of the day, what have we learned is that the concept of invariant subspaces allows us to search for very interesting spaces, one-dimensional subspaces that are invariant. And in those subspaces, you have the eigenvector as the vector that spans those subspaces, and the eigenvalue as the way any vector in that subspace responds to the action of the operator t. And the only response possible is scaling. So these are particularly simple vectors. If you know the eigenvectors of an operator, you know almost everything about an operator. If you know the eigenvectors and eigenvalues, you really know a lot, especially if you're working in complex vector spaces. That will not be the same in real vector spaces.